This is a summary of the Rice-Mele model we have discussed in the previous video. We have considered a chain with two types of atoms in a unit cell. The quantum mechanical Hamiltonian of the model, H, can be written in real space and in K-space. We found the spectrum of the eigenenergies as well as the corresponding eigenmodes, which are not shown here. There are special values of the model parameters m, u, and v at which the gap closes. For m equals to 0 and u equals to minus v, the gap closes at k equal to 0. For m equal to 0 and u equals to minus v, the gap closes at k equal to 0, and for m equal to 0 and u equal to v, at k d naught equal to pi. Following Thouless, we want to calculate the current that is pumped along the chain as we change the parameters of the model adiabatically, in a rate which is small compared to the gap. So in order to find the current, we had to define a current operator. So the current operator is given by j of k is given by dh to dk. I remind you that h is a 2 by 2 matrix. Here we had earlier k d naught. D naught was the size of the unit cell. I just omit that for brevity. Now the average current will be given by this expression, j of t, 1 over L. L will be the number of atoms in the systems times d naught, times the sum of all the occupied states which look in this way. U twiddle kt, dh to dk, u twiddle kt, minus meaning that these are the occupied states. Each state is described by its own current j, k, and t. I want you to notice that u has a tilde on top of it. So what u tilde is important. This is a solution of the time-dependent Schrödinger equation, and it should not be confused with the Schrödinger equation of the instantaneous problem, in which I freeze out the parameters lambda of t, freeze them out, and solve the time-independent Schrödinger equation. The relation between u and u tilde will be using the adiabatic approximation, which we'll do in the next slide. Right now, I remind you that what we have to calculate is the total pump charge, which is the integral from 0 to t of this expression for jt. And what we want to show is that the charge which is pumped is quantized, is an integer times e, the charge of a single electron. So now I remind you what is the adiabatic perturbation theory. I'm sure you all saw it in this way or that way. I just remind you what is the adiabatic perturbation theory for completeness. So we write u tilde in terms of u. There is this dynamical phase as a prefactor, and it's equal to u minus plus the correction, which is given by the perturbation theory, I divided by the energy plus at a given k minus the energy minus at a given k, u plus d to the t of u minus kt, u plus kt, and so on. The expression for the current, I remind you that we had j was, the average j was something like that, u times the operator j u. So what we get is that expression for jkt, I divided by e plus k minus e minus k, times u minus dh to dk, this because j was, remember, dh to dk. So this is the expression that we get for the current jkt. Let's continue. Now what I want to do is to further discuss how to express the h to dk in a certain way. So for that, we use the perturbation theory for hk plus delta k. So we expand hk plus delta k to hk plus the h to dk delta k. Then we use perturbation theory for the eigenstates of h as a function of k. So the first order correction for linear in delta k, u1 kt, which I just defined it as delta u minus kt, is given by u plus dh to dk, u minus kt, e minus k minus e plus k, times u k of t, u plus k of t, times delta k. Now I divide both sides by delta k, and I multiply from the left by u plus, and we get this expression for And we get this expression for this matrix element, where by definition, this guy is just delta U, the state delta U divided by delta K. So we get this expression for jkt minus I times dk U minus times U plus times U plus dt U minus kt. This is just a summary of all the formulas that we had so far, minus complex conjugation. Now this is not the final story. We can actually simplify this expression further. And this is done by using the fact that U minus times U minus is normalized, the fact that U minus is a normalized function. So that gives us the following result: dk U minus times U minus dt U minus Brian cat minus the complex conjugation is equal to 0. And in order to see that, I want to prove for you this result. So we start from U equal to 1. I take the derivative of that with respect to k. So it will be U is equal to 0, but this is nothing more than dk of U times U plus U dk of U, all that is equal to 0. Now a similar situation we can do for dt. dt of U times U is equal to 0. So U dt of U plus dt of U times U is equal to 0. Now if I move that element to that part of the equation, so I will have here equal to minus, and the same thing here. So instead of that, we'll put it here, so it's equal to minus. I'll multiply both sides of the equations, and I get that dk U times U times U dt of U minus the complex conjugation is equal to 0, which is exactly the formula that we have here. Now, using that and the fact that U alpha, when I sum on both plus and minus, U minus plus U plus, the cat and bra, that is equal to 1. So if I sum these two equations, I add to jkt simply 0, then I can remove this U plus here and the U minus there. And finally, we get that result for jt is equal to minus I 1 over L sum over k dk U minus k of t dt, the bra and the cat of dt U minus k of t minus the complex conjugation. So now we can go to the continuum limit, in which we send L to infinity and we integrate over k. We can write this expression for jt in the following way: minus dk over 2 pi bkt. And the expression for bkt is simply, I copy it from that expression, is given by that expression. We can further simplify this expression by writing it in the following way. So this will be the bra gradient of U minus cross the cat gradient of U minus, and by gradient we simply mean dk to dt. Now this term b is the Berry curvature. So we define the Berry curvature for this expression, and here Berry is checking that we do everything properly. So let's continue. We define the Berry curvature. This was the definition of the Berry curvature in terms of B, but we can also write it in terms of a curl of A. So we use the letters B and A to remind us something like magnetic field and vector potential. Now, this A is by definition given by bra U d to dl cat AU. L is either K or T. These are the components of A. And AL is the Berry connection. So now we have an expression for the pumped charge. Q is the integral from 0 to t jt dt, given by this integral on time and on the momentum of the Berry curvature bkt, and this will be our starting point of the next video, in which we analyze this expression to show that it's a quantized pump. So see you in the next video.